so let's go ahead and finish up. We did the earthquakes. So now let's go to page 296 and we'll do the pH. Example number 6. Okay, pH. Your pH is basically defined as this. This is your pH. Okay, and you've done this all in chemistry, right? pH, what is the range that pH can take? Can anybody tell me that? What is the lowest a pH can be? Nobody? Has anybody taken chemistry here?
Yes.
Okay, so how do you test the pH of a solution?
I use like a strip or something.
Yeah, you use what is called the litmus paper, right? The litmus test, right? The litmus test. And the pH will give you anywhere between 1 to 14. Does this ring a bell? What is a neutral solution? What is a neutral pH?
It's 7.
It's 7, right? Water, just plain water is 7, right? The lower the number, what does that mean? It is more what? More acidic, right? It's more closer to acid, whereas the higher the number, it's more closer to an alkaline, right? It's an alkali, right? Okay, all right, so is none of this ringing a bell to you guys? You guys haven't done this?
Mr. I'll give you 100 with you real quick. I did not pay attention much in chemistry.
I didn't take chemistry, so I have no idea.
You have no idea. Okay, so you are excused. What about everybody else?
I have not covered pH levels in chemistry. If I have, then I may have forgotten.
Okay, all right, okay. Likely excuses. Anyway, okay, let's move on. Example number 6. Some especially sour vinegar has a pH of 2.4 and a box of Legensickle baking soda has a pH of 8.4. What are their hydrogen ion concentrations? So for the vinegar, we have the pH was 2.4, right? So basically, what do we have here? We have, since this is that, we can say that this is going to be the negative over here, and then we could go put this under tens like that, right? And this would be basically this guy would be equal to 10 to the negative 2.4. Okay, and that's what they wanted to know, the hydrogen, the concentration of the hydrogen ion, right? So it's going to be this. For the other one, it was going to be what? It was 8.4, was it? 10 to the negative 8.4. Okay, that's going to be it. B, how many times greater is hydrogen concentration of the vinegar versus the baking soda? So it's going to be the vinegar over the baking soda. So it's going to be negative 2.4 plus 8.4, 10 to the 6. Right? It's going to be 10 to the 6. So C, by how many orders of magnitude did the concentration differ? 6 orders of magnitude right there, right? 6 orders of magnitude, right? It's 1,000,000 times more, 1,000,000 times more, right? All right, so that's example number 6. Let's do example number 7. So example number 7 is what we call Newton's law of cooling, okay? Newton's law of cooling. So what Newton's law of cooling covers is that if you put if you baked a cake and you brought it out and let it cool off, right? The heat's gonna dissipate and it's gonna eventually cool off, right? It's gonna eventually come to what? And in the end, where does it go to? It goes to whatever room temperature it was, right? Whatever room temperature it was, right? Or if you were going to boil an egg, right? If you boil an egg, what's the first thing you do when you are done boiling the egg? Can you ever tell me what you're supposed to do?
You turn off the heat?
No.
You put them in cold water?
Yes, you put them in cold water. Why do you put them in cold water? Because it allows for them to cool, right? That's one. What else is there? Does anybody know? It peels a lot better, right? The skin comes, the white filmy stuff in the egg comes off a lot quicker if you immediately dunk it in cold water, or sometimes you just put ice over it, okay? And what does that mean? So you have, let's say that you have, this is ice water, and you put the egg in here, right? And it's gonna cool off, right? So we're gonna call the temperature of the water, or the medium, the cooling medium, we'll call that the TM, right? And the temperature that the eggs goes into initially we'll call T initial, okay? So what determines how quickly this is going to cool? Can anybody tell me? Is it how hot the egg is? Or is it how cold the water is? Or what is it?
How cold the water is.
How cold the water is? But what if the initial temperature of the egg was only 15 degrees, whereas if the medium temperature was 10 degrees, versus what about the initial temperature was 100 degrees? So it's really not the temperature of the water, right? What is it? Be more specific. What is the driving force of the cooling mechanism here? Isn't it the delta T? It's the temperature difference, right, between the egg and the medium, right? Whatever you're using to cool it. Okay. So if you look at it that way, we can come up, or Newton came up with an equation that stated the temperature difference is going to be equal to the initial temperature difference to e to the some kind of t, all right, some kind of e to the at. So it's going to be decay away, right? The difference in temperature is going to decay away. It's going to decay like this. Okay, and this is what, in a nutshell, what Newton's cooling law is. So if you look at page 296 in the middle, there's a Newton's law of cooling, and it has something that is not like this. It does not look like this. Okay? I can tell you right now that it is easier for you to know it this way rather than what's in the book. Okay? So the delta T at any given time is going to be the temperature of that egg at that time minus the moderator temperature, or the medium, right? And the initial temperature difference was the initial temperature of that egg minus the medium. Like that, right? And, oh, you got K here instead of A, so we'll use K just to make it less confusing for you guys, all right? So it's going to look like this. Now, if I move the M over, it's going to look like this. And this is what I'm going to get. Now, that is exactly what you have in the book. Okay? So you can either memorize this, or you can understand it and make it look like this. So which one's easier for you? You can pick your choice. If you would rather memorize this, you may do so, or you can just go ahead and look at it this way. All right?
I think I would prefer the latter.
Yes. So most people, it's going to be a lot easier to do this. At the bare minimum, move the TM over here, okay? And then it becomes a little bit more intuitive, okay? But don't try to memorize it the way it is in the book, okay? So now let's go ahead and use this and see if we can go ahead and solve some questions. And again, this is the one that is always on the test. The Newton's law of cooling will always be on the test, okay? So you might want to pay attention to this one. A hard-boiled egg at temperature 96 degrees Celsius is placed into 16-degree water to cool. 4 minutes later, the temperature of the egg is 45 degrees Celsius. Use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. Okay, again, so let's look at it this way, delta T, delta Ti, e to the negative KT. Okay, so, and it seemed as though so the initial temperature is what, 96 degrees, right? So the initial temperature is 96 degrees, so initial temperature difference is going to be 96 minus 16. And at any given time, the temperature difference is going to look like that. And we have this. Okay, so we know everything here we need to know except for what? This is the guy here that we don't know. We don't know K, or we don't know K. And this is the guy we want to find. Okay, so we're going to have to somehow find K. Okay, now I am given that 4 minutes later, the temperature of the egg is 45. So when T is equal to 4, the temperature is equal to 45. Right? So I should be able to solve for K now. So I'm going to have, this is going to be 29, this is 80, e to the negative 4K. If I divide both sides by 80, I get that. Now I'm going to take the natural log of both sides. All right, if I do that, the negative 4K comes up. Negative 4K, natural log of E. Natural log of E is 1. So I have this. So K is going to be equal to natural log of 2980 divided by negative 4. And that'll give me what K is. Okay, and if I do that, it looks like K is going to equal to 0.253. So now I have the full equation, 0.253t, right? And now I know all this, so I don't need this anymore. And what was the final question? The final question was, when will the egg be 20 degrees? So the final temperature is 20 degrees, moderator is still 16, and we had 80 here, e to the negative 0.253t. 20 minus 16 is 4, divided by 80, this guy goes away. 4 over 80 is 1 over 20. Take the natural log of both sides. This guy comes forward, negative 0.253t. Natural log of E is 1. So this is natural log of 1 of that. Divide both sides by negative 0.253. And you can find your time. Okay, we'll see how that went. All right, let's do one more. And on this one, they're actually going to give you the data, and you're gonna have to go ahead and use the data to do a regression, it looks like. So example number 8. Example number 8. In an experimental temperature probe connecting to a calculator-based CBL device was removed from the cup of hot coffee and placed in a glass of cold water. First two columns indicate the first columns of table 3.23 show the resulting data for time in seconds since the probe was placed in the water and the temperature. Okay. Now they re-express that by subtracting the temperature of the water, the moderated temperature. So it's T minus Tm. So this was basically the delta T, right? That's a delta T there. Okay. So they're tracking the delta T there. All right. And blah, 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 blah. Estimate the temperature of the coffee. Okay. What would the temperature of the coffee be? Anybody want to take a guess? Wouldn't that be the T minus Tm, right? T minus Tm there is 63. So T minus Tm is equal to 63 on the first one. 60.3, I'm sorry, 60.3. And then the temperature here was 64.8. So if I subtract from this, won't I get the Tm? So it's gonna be what, 4.5? Looks like it's 4.5. Does that hold true for all of them? At time 5, it looks it's the same. And yeah, it looks the same all the way through, right? It's a 4.5 degree difference. So the water, the ice water or whatever the water was 4.5, right? So that had to be 4.5. Oh, it already says there, right? Estimate the temperature of the, coffee. Temperature time of the coffee. Okay, so let's go ahead and, so they want to know the equation. So the equation was delta T, delta Ti, e to negative KT. So we had the temperature minus 4.5. The initial temperature was what? What was the initial temperature? Does it give us the initial temperature? It doesn't. So you're going to go ahead and you're going to have to plot the time versus the delta T, and then you will do a regression. Can anybody tell me what kind of regression you're going to use? You're going to use the E, right? You're going to use the natural log, right? You're going to use the E, the power base, right? So if you do that, oh, wait a minute. Okay, so we're going to do, let's just do this. We can do this algebraically, I guess, if we wanted to. So let's do 2 of them. Let's do a time 2. We're going to get, I don't know what this guy is, e to the negative k times 2. My temperature was what? My temperature was, this guy was 60.3. And then again, time 5, I have 49 is equal to, again, I don't know what this guy is, e to the negative k to the 5. Right? So now let's look at this. I have 2 unknowns, delta Ti and the k. I have 2 separate equations, so I should be able to solve this. And the way I'm going to do that is I'm going to go ahead and divide both sides like that. And what that accomplishes is that this guy now goes away. Okay, so now I have 1 unknown. All I have to do is solve for k. So I get 60.3 over 49 is equal to e to the negative 2k plus k5. So it's going to be e to the 3k. Natural log, the natural log, 3k, natural log of e is 1. So if I divide this guy by 3, that'll give me k. Okay? So once I find k, I can put it back into one of the equations. I can put it back into the first one. All right, I can put it back into this guy here and find out what delta ti was, right? So what did I get for k? If I do that, I find that k okay, I find 60, what's this? Okay, I'm gonna let you guys do that. Oh, okay, does it give this solve for k here for us? No, it doesn't. But you guys can go ahead and solve for that and find out what k is, and then put that in and find the delta k, delta ti. Okay? But you understand how I did that? Which point did I use? The 2 points that I used, right? Okay. All right. So let's go ahead and do that. And then we have the logarithmic re-expression. Logarithmic re-expression is basically finding, or this is more, it used to be pretty important stuff where we could go ahead and take the log of one of the columns to re-express it to make it look linear. Okay, but nowadays the calculators have the logarithmic regression in it. So if you do L1 and L2 and you go to stat calc, one of the options would be a logarithmic regression. Okay, so you can use that and it will do it for you. So it's not as important, but still something you should know. Okay. So if you flip the page, go to page example number 9. Did they decide whether these data can be best expressed by logarithmic, exponential, or power regression? So how would you do that? You have x1, x and y. So in x and L1, you would populate x. L2, you would populate y, right? And then you would do a scatter plot. If you do the scatter plot, you get the figure 3.38. Okay, so it doesn't look like a linear is good here. Okay, a power would work. Doesn't look like it's going to be a logarithmic, right? Because a logarithmic would go like this, all right? So it's going to look like it's going to be a power or an exponential. Okay, but it doesn't look like an exponential because it's not going to go through 1. So I would go with a power regression. So if you did the power regression on your stat calc, when you do stat calc, you do a power regression, you will find that it works. And you can also, if any doubt, you can go ahead and compare the what. How would you compare which regression works better? What are you looking for? I mean, what we talked about now, that we just talked about now, was basically a kind of a feel thing. But what would you actually be able to say once you did the actual regressions? How would you compare the regressions? Which one is more effective? Is there a number that gives you, that your calculator will give you? Caden, is there a number when you do the L1, L2 and do the stat calc that you get that allows you to compare whether one's a better fit than the other one?
Like when you fill them?
Huh?
What are you asking? Like when you populate L1 and L2?
Yeah, when you populate L1 and L2, because then you did the stat edit to do that. And once you do that, you're going to do the stat calc. Stat calc is going to give you several different options, regressions there, right? How do you know which one fits better than the other one?
I'm not sure. Did you just try them?
Well, you would look at the R squared values, right? It's going to give you the correlation of the coefficient of correlation there. Okay. So you look at the R squared values. You look at which one has a greater R squared value. That will tell you which one is a better fit. Okay. So you would compare the R squared values. Okay. All right. So we'll stop right here for today.